Okay, so we are at the final two objectives of section 1.2, Mathematical Models, a Catalog of Essential Functions. And part of the library of essential functions that we'll need for calculus are the exponential and logarithmic functions. So exponential functions are functions of the form f of x equals a to the x, where the base a is a positive constant. Notice the difference between this and a power function or a polynomial function. Those have constants for the bases and variables for the exponent. Power functions have the variable is the base and a constant is the exponent, like x squared. But this is not that. This is 2 to the x, where the base is constant and the variable is in the exponent. The graphs of y equals 2 to the x and y equals 0.5 to the x, that is 1/2 to the x, are shown in the figure. In both cases, the domain is negative infinity to infinity, the set of all real numbers, and the range is the set of positive real numbers, 0 to infinity. And here, the big, difference between the two is the base, its relationship to 1. So here we've got 2, which is greater than 1. And in the other one, we've got 1/2, 0.5, which is 1/2, which is less than 1. And that's why its graph is decreasing as we read from left to right. 2 to the x is increasing as we read from left to right. These are the two families of graphs of exponential functions, the increasing one and the decreasing one, the one with base greater than 1 and the one with base less than 1. Exponential functions are useful for modeling many natural phenomena, such as population growth for a greater than 1, and for radioactive decay, a less than 1. So where you have growth, you're going to have the increasing graph. Where you have decay, you're going to have the decreasing. Logarithmic functions. The logarithmic functions, f of x equals log base a of x, where the base a is a positive constant, but not equal to 1, are the inverse functions of the exponential functions. They undo the exponential functions, and the exponential functions undo the logarithmic functions. Figure 21 shows the graphs of 4 logarithmic functions with various bases. Now, these bases are all greater than 1, and so we only see one of the two families of graphs of logarithmic functions, which are separated along the same lines as the base greater than 1 or less than 1. In each case, the domain is the set of positive reals, 0 to infinity, and the range is negative infinity to infinity, right? We have points for any of these. Pick any one of them. We'll just take the green one, log base 2 of x. For any of them, we've got points all the way up and all the way down. And so the range is the set of all real numbers. But because the graph is entirely to the right of the y-axis, it may look like it touches the y-axis, but it doesn't. The domain is 0 to infinity. The function increases slowly when x is greater than 1. Example, we have 4 functions here. Let's classify the following functions as one of the types of functions that we have discussed in this section, which is, several videos back. Well, if you don't get this one, then you're not a very good listener. F of x equals 5 to the x. Then we're going to have x to the 5. So that'll also test how well you've listened to this video. Then we got this h of x, which is pretty crazy. It's got a fraction, it's got a radical, and then we have a polynomial function. Whee! I just told you the answer. Okay, anyway, make a decision on all 4 of these. Well, 5 to the x is exponential. The variable is in the exponent. And the constant is what we have for the base. Unlike what we have in part B, the variable is the base and the constant is the exponent, and that's a power function. We could also consider it to be a polynomial function of degree 5. That thing is trivially classified as an algebraic function. I think it'd be more helpful to classify it as a radical function or a square root. Well, not a square root. The best way to classify it, I believe, is as a radical function. But yeah, of course it's algebraic. All of these are algebraic. And D, we've got a polynomial function of degree 4. 4 is the highest degree on the variable t. That will get it done for section 1.2, a library of essential functions.